Hello and welcome to another episode of TWiML Talk, the podcast where I interview interesting people doing interesting things in machine learning and artificial intelligence. I'm your host, Sam Charrington. Today we close out our NeurIPS series and our 2018 conference coverage with this interview with Nando de Freitas, team lead and principal scientist at Deepmind and fellow at the Canadian Institute for Advanced Research. In our conversation, we explore Nando's interest in understanding the brain and working towards artificial general intelligence through techniques like metalearning, few-shot learning, and imitation learning. In particular, we dig into a couple of his team's NeurIPS papers, playing hard exploration games by watching YouTube, and one-shot high-fidelity imitation, training large-scale deep nets with reinforcement learning. Enjoy. All right, everyone. I am here with Nando de Freitas. Nando is a team lead and principal scientist at Deepmind, as well as a fellow of the Canadian Institute for Advanced Research, or CIFAR, as you might know it. Nando, welcome to This Week in Machine Learning and AI.
Thank you. Thank you very much for having me here. It's such a pleasure.
Absolutely. It's great to finally get a chance to speak with you. I know we've been trying to coordinate something for a while now, but fortunately NeurIPS brings us all together. I'd love to hear a little bit about your background and your path into ML and AI.
Yeah, so I got into ML and AI a very long time ago. We're going back to prehistoric times here. So actually it was in 1994 when I was an undergrad at the University of Witwatersrand in Johannesburg, South Africa. And a professor, my control professor, introduced me to this thing called neural networks. And I was fascinated by neural networks and tried to learn as much about them as possible, coordinate maps, backpropagation, and ended up implementing something that eventually went into hardware, and it became a controller for pneumatic control valves. And with that work, I eventually even made it to an international conference. That was, I still remember, a 26-hour trip from my home to my first conference in Washington. It was extremely intimidating because I was this kid from Africa, and there I was meeting all these big shots and people that I thought I would never be able to ever hang out with. They were like heroes to me. Some folks like David Heckerman, Andrew Bartow, and a few others, like very prominent people in the field. It was a great experience. It was intimidating. And when I went back to South Africa, that made me want to do a master's. And so I continued my work with neural networks. And eventually through that, I was able to apply to universities. And I got lucky. I got a scholarship to Cambridge. And I went there and I continued working on Bayesian neural networks, and that was my PhD. And it became very statistical. Ended up going to Berkeley, and by just fluke, my supervisor there, Stuart Russell, was in computer science, so I somehow became a computer scientist. And eventually, after 2 years there, I moved to UBC, where I was a professor of machine learning, introducing some of the undergrad courses that you probably have seen on YouTube. And it was there that I first started participating in the CIFAR program. And this was organized chiefly by Professor Jeff Hinton. And the goal back then was to understand the brain. And this was so amazing because it was suicide in those days to put a grant with that title. You would not get tenure. This was like a crazy thing to do. But fortunately, some of the key leaders in Canada believed in that ambitious vision. They're still there and they continue inspiring us. And that's what we did. We embraced that vision. Our research sort of steered toward that at the time what seemed a more difficult path, even though now it seems it's very easy in retrospect what we do. Yeah, and that's kind of how I got into deep learning and how I got here.
Have you since returned to applications in control systems?
Yeah, I continue doing a lot of that.
Okay.
So a lot of the knowledge that I gained from my undergrad in my master's in control, things about certainly all the mathematical thinking about the differential equations, knowing how to sort of map things to frequency domain and so on, but as well as being able to do things like PID controllers.
Right.
Those are still the things that we use today, like when we try to control robots, and we might use neural networks these days to sort of set up parameters automatically of different PID controllers. But all that background has been very useful.
Yeah, those were some of my favorite courses from grad school: PID controllers and hysteresis and all these different control theory things. But I've had the impression that stuff is works so well, and there's such a need for a more deterministic response for a lot of the applications of this, that there hasn't been much in terms of neural network applications for that. But it sounds like you've been doing that for a while.
Yes, no, there's quite a few people that work with it. So so control and the sort of combination of classical control techniques with the new sort of the reinforcement learning techniques. It's actually a very fruitful area of research, and I think a lot of the work that folks like Peter Abil at Berkeley do, like Michael van der Pan at UBC, Ima Chodorov at the University of Washington, it all sort of involves a bit of a marriage between the classical techniques and the new techniques. And I think there's still a lot we can learn from classical control as well in terms of robustness and constraints. Because as we build controllers, we want to make sure that they're safe, that we can verify them and so on. So these continue being challenges that we have to address in order to deploy the technology.
So tell me a little bit about your research interests. It sounds like you kind of dabble in a lot of different things, but how do you kind of characterize the general scope and direction of your research?
I think fundamentally, it's still the same that it's always been. It's trying to understand the brain, trying to understand what it is to be me, what it is for you to be you, and for us to be engaged in this discussion. That's the real goal. And of course, we have to sort of break this problem in order to be able to attack it. We have to think of how to formulate the question, and often that's what leads to things like RL. You can specify tasks and cost functions. So it's a language to talk about the problem. We can sort of think of it in terms of cognitive abilities that we have, like memory or imagination, curiosity, and so on. So there's many ways to attack the problem of understanding the brain. And I think this is a huge problem, and there's so much yet to be done. And I've picked a few directions. I see my colleagues have picked other directions, and I think it's going to involve many perspectives for us to eventually come up with an understanding at many levels of abstraction of what it is, in a sense, to be human.
Do you think that our understanding of the brain has benefited our understanding of machine learning, or the practice of machine learning, more or less than machine learning has benefited our understanding of the brain?
That's an interesting question. So it is very clear that the understanding of the brain has helped us get here. A couple years, actually 4 years ago, I went to Japan, and I had the honor of meeting Professor Fukushima, who was the author of the neocognitron, which is essentially the convolutional neural network architecture that we all use these days. Jan LeCun added backpropagation to that architecture, and that kind of is what brought us here. That was a success story in vision and so on. When I spoke to Professor Kitagawa, he mentioned that what inspired him to do that work was the work of Hubel and Wiesel in neuroscience. And when he worked at this institute, I forget the name of the institute, but they put neuroscientists and computer scientists together. And it was through this combination of different disciplines working together that he found out about these results in neuroscience and decided to code this model. So I think neuroscience has played a huge role. I'm told the set of Wright was also influenced by cortical models of cells and so on in order to propose LSTMs, which is also one of the key components of machine learning. Has it helped the other way around? That's a much harder question. I mean, clearly with the success of backpropagation and so on, a few researchers at MIT, for example, they went on and they were starting to use that new knowledge to explain how the visual cortex might be working, and so on. I also think more recently, folks are starting to, like Conrad Cording and so on, trying to look at the research that has happened, not just in machine learning, but the combination of statistics and econometrics and machine learning and biostatistics, looking at things like causal modeling in order to go back and try to understand, to try to formulate a theory of how it is that we should approach neuroscience and what sort of findings we're looking for. So I think to some extent it also has panned out the other way.
Yesterday at the poster sessions, I was checking out one of the posters that was making kind of a strong correlation between what's happening in the brain and image processing and CNNs. And I'd always thought of neural networks in general and CNNs as kind of quote unquote inspired by the brain, but not really, exhibiting a very strong correlation. But they were, talking about layers as like V1, V2, V4, whatever, and IT, which presumably are relate to a model of how we think the visual information is processed in the brain. I didn't realize that there was that strong a correlation between these two fields.
Yeah, there appears to be. Certainly, for example, at CIFR, so every year before NeurIPS, there's another workshop that takes place. It's a 2-day workshop called the CIFR meeting. And actually, I just came from it. There we've always have a combination of invite people working in neuroscience, as well as people working in computer science, engineering, physics, and so on, people from different areas, from causality, etc. And we try to sort of use everyone's insights to sort of advance what mainly to choose what research areas to explore next.
Okay.
So I think neuroscience has always informed what we do in machine learning, and machine learning, I think, also informed neuroscience. So certainly, at least at that meeting, that's the case.
So the driving motivation is to try to understand the brain, so that kind of reverse part of the feedback loop. And one of the recent areas that you've been exploring to help get there is been imitation learning. And in particular, you are a contributor to a paper here that's focused on third-party imitation learning.
Correct.
Let's just dive in. Tell us about that paper. What's the motivation there?
Okay, so I'm excited about imitation because imitation is something that we all do. A lot of the things we learn are through a process of imitation. And in particular, I'm interested in a form of imitation called fuse shot imitation.
Okay.
Which is sort of follows from, you can sort of think of it in terms of meta-learning. So the idea of meta-learning is evolution is a learning process that happens at a very slow scale, and it produces biological machines, us. Machines that are capable of learning very rapidly with very few data. We don't experience that much data throughout our lifetimes. And so we kind of want to do the same thing. We want to sort of learn machines that can imitate very rapidly. So we train them through a very expensive process, but then we can deploy this machine and someone can demonstrate something to this machine, and then the machine is able to do that. Now, then comes another question. of when you demonstrate, your demonstration might be with different objects, so different hands. And so you need to now deal with the third person here. What we mean by that is that you might have learned to do the task using, I don't know, robot hands, and now you have to watch human hands doing the task, and then you have to, the robot has to imitate. So very much like when children can imitate a dog by using their foot to scratch behind their ear, and they're able to remap from one type of body to another body quite easily.
And the contrast is, I guess, first-person imitation learning, which is, for example, you're looking at the actions that someone is playing in playing a game and learning based on those actions, as opposed to just watching them, quote unquote, from a distance.
Correct.
Right.
So you precisely. So in first person in Atari, for example, if you're playing Atari, first person, you would collect data from playing the game in Atari. You would try to fit a model to it. In third person, what we do is we actually go to YouTube and we look at people playing the games. And it's third person because there's a bit of there's a domain gap. In YouTube, sometimes this video is, well, the video will definitely be of a different resolution, different color. It will have ads inserted. It will, it has all sorts of other artifacts. And so we need to be able to remap from that thing in YouTube to our domain so that we can play the game. And inspiration for this for me was like watching a child, actually my nephew, spending a lot of time playing. What's that thing that kids play?
Minecraft.
Minecraft, yes. So he spent a lot of time watching Minecraft, and I remember telling my brother, "You're not worried about this?" And my brother's like, "Oh no, this is actually very good. He does really well in school when he does this sort of thing." And what he does is he watches these videos and then he goes and plays. And so I realized, well, that makes sense. This is what we should do. Right. And so then I work with these very gifted scientists and engineers who took the idea and went and implemented this in the context of Atari. I think this is sort of an initial step, which is more than anything just a demo of what could be done. I think there's a lot of footage in YouTube for all sorts of things. And so the hope would be that we eventually could train, say, robot manipulators or in simulation or with real robots to be able to watch YouTube and be able to, even though there's a domain gap because they're watching different human hands, say, tying knots, and then they would have to then tie knots themselves. That's not actually easy. Like tying shoelaces, for example, is something that even 6-year-old humans struggle.
Interesting. I think I've come across videos that or examples of research that is trying to do some of that kind of thing, but not with actual instantiated robots, but like animation. So watch a video of dancing and try to get the stick figure to dance or things like that. It seems like there are a lot of parallel activities kind of going after the same type of problem.
Correct. So a lot of this can be done in simulation, and in a sense it's easier to do it in simulation. Robots are basically machines. They're complicated. It's like, and they're not produced by typically a man. They're like cars, except that with cars we have these big companies that produce these nicely engineered machines. Right. And robots are more like cars when they started appearing in the world. They're sort of makeshift Frankenstein type things put together. And so they break down a lot of the time. It's very hard to do robotics. The software is somewhat lagging and so on. But nonetheless, it's interesting. Manufacturing keeps being one of the, automation in manufacturing keeps being one of the driving forces behind, control theory, in fact, and control and machine learning.
And so has your work in this area with playing the Atari games, is that also still in simulation, or do you have some robotic thing playing the game?
So that's in simulation, but we have been doing other works, also doing imitation, and in particular doing this few-shot imitation, where we use simulation, so physics accurate simulation through an engine called Mojoko. It's kind of what OpenAI Gym uses. And then we also use real robots to do these sort of things. And so we've been very interested in this sort of few-shot imitation, which is basically imitation with a few data. The challenge here is, and the challenge being the challenge of what I call few-shot meta-learning, is to get a machine and being able to sort of demonstrate something new to the machine with novel objects, with novel motion, and have the machine be able to do the same thing. So if you think of, I want to go beyond building machines that are like classifiers, like a CNN, and instead they're learning machines. They're machines that I can give to someone at the factory, and that person can then modify the machine via demonstration or via some formal language or natural language, and get the machine to do something new or do it slightly different. So I always think of the next generation of AI machines as adaptable machines or tools that learn. So it's very much like when we give tools to animators. I think to people in factories and so on, what we need to do is give them tools that they can adjust and adapt and sort of become much more productive, so they don't have to do all this sort of low-level coding in order to, or change hardware, etc., in order to deal with the fact that maybe the lids of their water bottles have changed in size.
Right. So when we're learning as humans, one of the things that we get to take advantage of is this relatively vast amount of quote-unquote common sense that I guess you can kind of think of as like transfer learning, in a sense.
Yeah.
In the context of few-shot learning, is there, in your research in particular, is there a starting place? Is there some base that we've taught the agent via, you tell me, or are we just starting from scratch with a few examples and saying, go figure this out? Like, what's the base?
Yeah. So you're absolutely right. Transfer is very important. So I would probably need to unpack what I mean by few-shot learning. Okay. So few-shot, I mean, it has to learn from few data. And then meta-learning is, there's this assumption that the learning is going to happen at least in two phases. There's going to be a very expensive phase, which involves many tasks. We want to build machines that can do many things, not one thing. So we train it to do many things. And there's different ways to do this. So, but we should be thinking about this as evolution, and evolution leads to what some people call priors. It's an initial state in your brain. When you're born with the faculty of language. You start with some sort of prior. There's still a lot of discussion on how to best do meta-learning in practice. And so there's this long process, and then there is also another process, which is the fast learning, which just with a few data, you should be able to learn to do something new with new objects or with new behaviors. So this is very important for robotics because unlike simulation, robots cannot afford to do repeat a task a trillion times until they get it right. And so it's important that they learn rapidly. So the name of the game then is maximize generalization while minimizing the amount of time needed to learn.
In which of the two phases, or both?
Actually in both phases, but particularly in the second phase, you sort of assume that you will be given very few data and you will have very little compute power and you will have to come up with a solution very quickly. And of course, if you haven't in the first phase constructed a representation that allows for abstraction so that you can go to, so you can sort of easily move to new tasks, then this is not going to work. So it's important that whatever representation you come up with, that there be sort of these In causality, people call this, like Bernard Sholkoff and recently Professor Yoshua Benji here in Montreal, they call this sort of the independent mechanisms. We also often refer to this as concepts, abstractions. And so by having these concepts, abstractions, or programs, I did some work before on something called neural program interpreters that I'm so very excited about, which is trying to understand these modular components of things in the world, like behaviors, programs, objects, and so on. So if we have that, and at the same time we don't want to hard code this, we want to learn this. So I think that's important. Then we have some much more hope that we will be able to generalize to novel objects and so on. So we'll be able to reuse some of the knowledge. So we'll know, if we had knowledge, for example, of physics, then whether this new task involves dropping something, then it doesn't matter whether it's an apple or a watermelon or a piece of chalk. If you open your hand, it will drop. You can predict it because you have an understanding of the laws of, at least at an intuitive level, you understand the laws of physics. So we definitely need abstraction. So it's few-shot meta-learning, but in order to get generalization, we need abstraction. We need to have a causal understanding of the mechanisms in the world.
Kind of taking a step back, we've got few-shot, meta-learning, imitation. All of these are part of, they're brought together to try to solve this problem. Is meta-learning kind of like the core challenge? And if you figure that out, then the other two are easy, or do they each kind of contribute their own unique challenges to the overall picture?
I think they're all different perspectives of looking at the same problem, which is like, well, how does the brain do it? Okay. So the meta-learning perspective is very useful, but of course, it still leaves open the question of how do we choose the representation. Likewise, we do some reinforcement learning when we do imitation sometimes. Sometimes we do supervised learning. But whether you do reinforcement learning, supervised learning, or whether you choose to think about problems in terms of reinforcement learning and off-policy learning, or you instead choose to think about them in terms of causality and counterfactuals, it's a matter of taste. It still leaves the question of what are the representations. So we still have to figure out what are these sort of independent representations and how to combine them in order to solve tasks. So I think all these different perspectives on the problem are very useful. The multi-agent perspective is also very useful because the most interesting thing at NeurIPS is not like the objects around, it's the people. People are the most interesting in our environment. A lot of these abstractions that I'm talking about, they're only possible with people. We can talk about a podcast because even though podcasts are things that, or perhaps a better example is we can think about today, Wednesday. There's no such a thing as Wednesday in the world. Wednesday is a construct of our minds. It's an abstraction that we humans find useful to communicate. And so eventually we do need the multi-agent perspective. And another sort of thing that sort of comes into this, that's sort of important in third-person imitation, is I'm able to, say, observe you, and you have a slightly different body than mine, and I have this sort of third-person view of you. So I'm looking at you, and I can see your whole body and parts of your body that you can't see. I also have my own sort of perspective, and I know what I'm feeling, for example, in my fingers, and I know how cold this room is. And
apologies.
And no worries. So the interesting thing is that so if you think of, I have a third person view of you, and I have a first person view of me. And through that, I can have a first person view of you. So I can more or less predict how you're finding the temperature in the room. I can probably predict what you're feeling in your fingers right now. And at the same time, I can also do the third person view of me. I can sort of step out of my head and imagine me sitting here in this chair ranting at you. And so we then end up with this 2x2 matrix. And eventually, I think this being able to sort of step outside of my mind and to know that it's me here talking to you. And to be aware of that, I think is very profound as part of understanding what is intelligence and how do our brains work. Because this is about knowing how I relate to the world. How do I know what I know? It's to know what I don't know, to know what I don't know. It's we're getting to this question of awareness. To be aware of your knowledge is something none of our machines have at present kind of done. And I mean, in fact, if we going in this direction, we are not too far from, dare I say, having a stab at understanding consciousness. Because that's to some extent, and not in a metaphysical sense, but to a computational, we're moving toward a computational definition of consciousness here. And there's a few scientists working, say, on attention schema theories and so on, that are starting to actually believe that it might be possible for us to start talking about. We already talk about like for example, a neural network policy with RNN. The internal state is a subjective state. And some of the work that I've already done with Misha Daniil, one of the researchers I collaborate with, shows that the models have an internal representation of the world even after they've no longer in the presence of that world. You know, sort of if they touch an object and the hand lifts, even a while later, there's still a memory of the shape of that object in the internal representation of the recurrent neural network. And so if we go one step further to there being awareness in that neural network of what it knows, that it knows that there was this object and it had a representation. When we start combining this with with abstractions, with counterfactual thinking and so on, I think we are getting very close to intelligence. The problem is we still don't know how to get these abstractions in order to be able to do third-person imitation and in order to be able to get good awareness models of the world.
So when you're pursuing a line of research like the third-person imitation learning, can you walk us through, the various phases of a project like that? How does it evolve?
So this one in particular, it's fun. You go collect videos of Atari on YouTube, and because the first thing you need is data.
Yeah.
So one initial state is coming up with representations that, whether it's the video on YouTube or whether it's the video that you can generate by playing the game in your own emulator in the lab. The representations in both domains are such that they are equivalent. So we call this sort of so one of my collaborators...
Which of the two that are equivalent?
The representation. So it's just the idea is to build neural networks that will, whether they look at a YouTube video or the actual video in the emulator that I have, they will produce similar representations. Okay. So the question is, how do we train this? Because we don't have supervision, and it's not an RL problem. It's something that we're now referring to as self-supervision. Okay. And so one of my collaborators, Yusuf Aitar, went to the YouTube videos, and he came up with a technique, that's contrastive learning, that allows us to be able to learn these representations. So he, for example, tries to predict whether a video frame appears before or after a recent video frame, or he tries to classify how many steps ahead is one segment of video from another segment, or whether the audio, which is an important part of Atari that we never get to see much of, whether the audio signal happens at the same time or not as the video signal. And through just these very basic checks, you can sort of formulate training labels, essentially. You can train a neural network. The typical techniques that we use there, the sort of contrasting what is right versus what is wrong, is basically what we call contrastive learning, and there's been many techniques for doing this. Max margin, maximal likelihood, in fact, is a form of doing this. And in fact, this is what kind of led to also GANs. Was that this kind of research of being able to sort of try to have a classifier that is telling you what's sort of real, what's not real. And
so you've collected the video, and I'm still not very clear on the,
so
the two representations.
Right,
one representation is the one you've built up from the YouTube videos. What's the other?
So because we're using videos that are very different with different players with different, the different sort of, all the videos will all have different appearance. But through learning the representations like this, we're able to get to embed the videos into vectors that are the same for all different variations of the video. And once you have such an
embedding on a frame by frame basis, or segment, or entire video, or something else?
Typically on a frame by frame basis, but you could sort of do this also. Conceivably, you could try to do this over sequences also. And with this, now if you have a trajectory in YouTube, now you can map this to a trajectory in latent space, in the sort of embedding space. And now this is essentially the trajectory that you need to follow when you play Atari. So then we use this trajectory as a reward signal, and then we just do reinforcement learning. And here Toby Pfaff, the other collaborator, just went and tried a couple reinforcement learning agents, and then it sort of learns it's using the trajectory as the reward signal, and it tries to follow it by taking actions in the game. So essentially all we've done is we've used the data that we observe in the world, solving the task in a slightly different setting. We call it with a domain gap, and we first learn the features, and then once we have those features, we can use those features to construct a reward function, and then we just maximize the discounted sum of returns in order to solve the game.
Okay. You mentioned that the videos that you come across have different levels of quality, and I thought you said something like different colors or levels of noise, correct, or whatever. Do you do any pre-processing, like domain adaptation, or anything to augment the data in some way?
Yeah, so in effect, the self-supervised learning is a form of domain adaptation. That's what we're trying to find features that are sort of common for all these domains. In Atari, the domain gap is not that big.
Yeah.
So it's somewhat easy for us to do some processing of the video scale and so on.
Okay.
What we will need to do is really address, and there's been a few papers, but this is still, I think, largely an unsolved problem, is be able to just watch a few videos of someone in YouTube doing something like pouring liquids, and then be able to get a robot, whether in simulation or a real robot, to also pour liquids. That is very hard to do. And in terms of mapping human hands to robot hands doing the task. There's a few nice efforts recently. Chelsea Finn has done some good work in this. We've sort of been looking at this as well. OpenAI has also some works. But I think we still have a long way to go before solving the problem.
And so what's your sense for what the next step is, the next piece of that puzzle?
So I think it's one of the things that I'm going to be betting on will be through coming up with better representations. And currently there's two sort of hypotheses here. One is just make the networks bigger.
Right.
And so the big networks is something we explored recently on a paper that we actually just put on archive recently with an algorithm called MetaMimic. The idea of MetaMimic is it closely imitates a demonstration. Like we in fact call this high-fidelity imitation. So you try to do something precisely like a human would do.
Okay.
So, and the idea is we're going to learn to do what humans do precisely for many, many tasks. So far we have only done it for one task with variation in the task, but the intention is to do this for many tasks. If you can learn to do one-shot imitation, sort of imitate many tasks. Then at test time, we show a new task with new objects, and then you check whether we can still imitate. So we've in effect test generalization. Now, what we found when training MetaMimic is we had to keep making the networks bigger in order to improve generalization on the test set. Typically, RL researchers haven't focused much on generalization, and this has changed recently over the last few years. And I'm actually glad to see our colleagues all sort of embracing these generalization tests. And what we're finding is here it becomes really important to make the networks big. However, we didn't know whether we could train the massive networks that we trained for perception, for things like vision and so on, to also do control. But in this work, we found out that it is indeed possible. If you have enough sort of these demonstrations, it's possible to train, like in our work is the largest ever trained neural networks to do RL. And by orders of magnitude larger than any pre-existing network. Most of what we did before with Atari and so on usually was with 2 layers neural networks.
Okay.
And in fact, Professor Todorov even complained about this and at one stage. I think if we are going to be doing control from pixels, or from pixels and ego motion and so on, it's very important to use large network architectures and to learn how to model them properly and how to train them. So the reason why we chose to go this way with MetaMimic is because if you observe children, when humans are solving a task, if they introduce irrelevant steps in between, children will solve the task, but they will also do the irrelevant tasks. Whereas a few experiments have shown that, I think with chimpanzees and bonobos, that they will go and solve the task immediately. They will not do the irrelevant steps.
Okay.
So humans have this propensity to what psychologists call over-imitate.
Okay.
And essentially, this is the strategy we're following at MetaMimic. So build a very big network that will imitate precisely millions of things.
Okay.
And that will allow it to sort of build into this model the capacity to, when shown a new thing that it had not seen before, it can just from one single demonstration repeat what has been done.
Okay.
We also found that these models can also be further trained with RL to solve tasks more efficiently. So that's one way to go that I'm going to explore. Just very big networks. And of course, there's a lot of engineering that goes into big networks. We have to put a lot of thinking into normalization and so on. So it's not, when we say big networks, it should not be understood that this is brute force engineering. On the other hand, one requires very precise engineering in order to train these big networks.
Okay.
That certainly has been my experience with some of our work on liberating, as well as some of the brilliant work that Deepmind has put out on big GANs, using GANs as generative models recently. On the other hand, I also want to sort of come up with representations that are more compositional. So that's like the neural programming interpreters work that I did with Scott Reed a few years ago. And that some folks like in Stanford, have used to build things like neural task programmers that are able to actually do very sophisticated control just by exploiting modularity, sort of program modularity, as well as to, sort of being able to break tasks into subtasks and so on. Yeah, that's going to be a continued effort. I think I'm also thinking that in terms of building many causal models, many small modules that you can then combine. And if the small modules are doing the right thing and they have a good understanding of, a good understanding in the sense they're causal representations of the world. And so, but by combining them in ways which we still have to devise, we should be able to get much larger models that can still represent the world and be able to generalize much better, because these models will be compositional. They will be able to have this combinatorial reuse of the components.
When you describe the first of those two directions, building out these much bigger networks, you made reference to kind of staying in the pixel domain. Do you see efforts what are the alternative approaches that are being explored, if any?
There's two different philosophies. There is the learning from scratch philosophy that tries to learn just from pixels.
Yeah.
And I often find too much from just pixels. In fact, if you're doing grasping and so on, it's important that you don't just have a monocular image, but you have stereo. So depth is a very important cue in order to grab things. And you just have to try to grab things from a single video, monocular video, to see how hard it is even for humans to do it. So there's that. There's, of course, touch. Haptics, and there's the fact that we have little hairs in our ear that allow us to know the accelerations of our head and so on. So we have a lot of internal gyroscopic information.
I guess I'm curious less about kind of multi-sensory and more, is there a direction to, I think the weights and activations in these networks kind of form concepts, but we don't necessarily force them to form concepts that are meaningful to us or abstract in any way, and I'm curious if that is a direction that people are pursuing.
Yeah,
does that make sense?
Indeed. So it's indeed there's two orthogonal things here. One is to sort of indeed go for multi-sensory perception and then learn these networks to conduct actions. And this still is the big open question. Like for example, in robotics, with like these competitions with flying drones. In a way, that's an easy problem because the drone doesn't have to touch anything. So, so there's no contact forces. This should be an easy control. It's an easy control problem if you know the state of the world. What makes it hard is that they have to do this. If they have to do this from pixels, navigate from pixels, and if there's people in the background that are moving and lighting changes and so on, then becomes incredibly hard, and it's still by far an open problem. So perception has not been solved. And that's essentially what this tells us. Or perhaps we're not using the right sensors. We should, and so on. Now, the other side of this, the argument is also what other folks are doing is they're sort of saying we shouldn't be learning from scratch all the time. You should in fact use that we have already learned some modules, some perceptual modules or some action modules, some controllers, and sort of learn to reuse the components. And that indeed, I think, is a very promising area. If you, certainly if you've learned controllers to achieve a task, it's possible to reuse them. And here controllers, you can think of them as also like sub-programs, and we can combine them. What we haven't done well yet is being able to learn a representation of something like an object, and then being able to exploit it, that representation, keep it in be able to harness it for future, to build future representations, to augment, to keep learning continually more and more complex representations, and be able to manipulate those objects. That is still an open problem. We don't quite know how to build this type of modular architectures. And there's two philosophies. There's people who try to model this by learning everything from scratch, and then there's people who, of course, try to inject much more domain knowledge. And they argue with each other as to who is right. But we've seen a lot of these debates in Twitter especially. But I think the verdict is still open. It's good that there's different perspectives on this.
Well, Nando, any advice or words of wisdom or pointers for folks that are interested in kind of digging in a little bit deeper into this area? Or closing thoughts?
I guess come to NeurIPS and iClear, and then it's sort of get to know, watch this podcast, listen to it, and there's also brilliant courses online like Andrewing and so on, so where you can sort of get into this sort of material and get a much better understanding of the material. We also organize summer schools. We, as in many researchers, volunteer throughout the year to teach summer schools all over the world. So here in Canada through the CIFA program, Lately, I've been involved with teaching a summer school in Africa called the Deeplearning in Daba, which is a great initiative because, and I think that is a parting thought that I want to bring into this. AI is a set of very powerful techniques. AI will be very influential in our world, not just the tech world, but AI will shape politics, AI will shape our economies, and so on. It is essential, it is of paramount importance that everyone has access to AI. If currently there is very strong biases, women are underrepresented in AI. There's a huge underrepresentation of certain races in AI, of certain continents in AI, and we need to address these imbalances. We need to address them for two reasons. One, we want to build tools that are fair. We want to make sure that AI is for all of us, not just for the few. And the other reason is because some of the people that have been marginalized from this actually have a lot to contribute. We often look at Africa as there's this wall that hasn't participated in the machine learning conferences. This year at NeurIPS we have at least 2 papers that I know of that came from Africa. So by helping a bit, going and volunteering there, we can sort of start reaping the benefits of their contributions. And there's lots of things that came from Africa. Gaussian processes were invented at my university by Professor Krigg, and it used to be called Krigging. EC2, if you actually look at the history of AWS, Africa played a big role in it. You know, this were people in South Africa working on this that have given us the infrastructure that now pretty much holds all the data from all banks and nation states and so on. It's important to also address the problems in Africa that we haven't even thought about because we haven't gone there. Things like translation. In South Africa, there's 11 official languages. In other countries in Africa, there's like 50 languages. When people tweet, they usually use 3 languages mixed. So translation is a huge problem. And so when you go there, you learn this, and then you realize, oh, it's important to sort of start working more on unsupervised machine translation and so on. There's also other problems. Like one, and I'm really going off track here. This is a very long. I apologize for having gone this long. Another problem that I thought was very interesting in going to Africa 2 years ago was when I learned about Mom Connect. So with Mom Connect, moms essentially get enrolled when they go to hospitals into this messaging service. And throughout Africa, people use these very cheap old phones that we used to have here. And they can still text and communicate quite efficiently. In fact, the service plans are not as expensive as here in Canada. so in many ways, they have leapfrogged our inefficiencies. And what they can do is the doctors can send them messages, reminders of what to do after the child is born and so on. And they can also, if they have questions, they can text the doctors. So for example, they could text the doctor, and this is like an example of what happens. Like, I've given water to my child all day and all night, but the child keeps throwing up the water. At that stage, the doctor can simply say, boil the water. Provide that sort of basic advice that will save a life. And in fact, if we want to have a huge contribution to the health of people on our planet, those little things are the things that sort of matter the most. And you can learn about them when you go and include people from other communities. And then you see the wonderful things they've already done to address this problem. So they actually can contribute a lot of insights into the development of machine learning tools.
Well, Nando, thanks so much for taking the time to chat. It's great to get to speak with you.
Thank you very much. Thank you for listening.
All right, everyone, that's our show for today. For more information on Nando or any of the topics covered in this show, visit twimlai.com/talk/213. You can also follow along with our NeurIPS series at twimlai.com/NeurIPS2018. As always, thanks so much for listening, and catch you next time.